This final presentation for ME452 will be on the foldable scooter. A foldable scooter is a compact personal transportation device that is easy to store and transport, with a folder frame enabling a smaller size, convenient for commuting short distances. Adjustable handlebars allow for steering and for different user heights, and there's a platform for standing support. Foldable scooters include 2 to 4 wheels for movement, and there's different versions available, including electric. There is an estimated demand in the US of over 5 million scooters per year, with a global market size valued at over $70 billion US. Market trends show an increasing popularity for electric scooters, and scooter brand Razor has sold over 50 million scooters in the last 25 years. The primary consumer market for foldable scooters are children, teens, and young adults, as well as commuters such as college students and young professionals who use them to navigate urban areas. The secondary market for foldable scooters include recreational and competitive users who use foldable scooters at skate parks or on rougher terrain. We now see an exploded view of the scooter along with the corresponding list of parts. Pictured here is our FAST diagram. Our main functive branch involves controlling the mobility of the scooter. Our first assembly sequence begins with base assembly, attaching the base plate, rectangular tube, and flange. That's followed by our rear wheel assembly, lower handle assembly, front wheel assembly, and finally, upper handle assembly. Our second assembly sequence begins with our base assembly, followed by our lower handle assembly, front wheel assembly, upper handle assembly, and finally our rear wheel assembly is added. When comparing the two sequences, we found sequence 1 to be more advantageous, although sequence 2 is better for testing sub-assemblies due to the early addition of the front wheel assembly. The early addition of the handlebars makes it much more awkward to transfer and handle, leaving sequence 1 to be much better on that front. The function component mapping matrix shows that most components serve only 1 or 2 functions. The function change direction is served by 7 different components, and the function support the rider is served by 6. This could be a great opportunity for part consolidation and a redesign for more efficient assembly and manufacturing. Our quad chart is based off of both the manufacturing and assembly costs of the part as well as the functional importance, used to help us consider what parts to eliminate and know what parts we should keep as they are. Our functional differentiation table separates our product functions into those common for both our primary and secondary customers, as well as those different for both groups. Both groups of customers cared about the convenience and dependability of the scooter. However, the functions that govern the way the scooter is ridden vary for each customer group. The component commonality table is derived from the functional differentiation table as well as the function component mapping matrix. It's important to note that the hinge was not considered a module, as the spring is the only platform integral to its use. Here we have 2 variants of our foldable scooter design targeted at the primary and secondary customers respectively. For the primary customer of children and commuters, we have a basic design with a smooth surface for casual riding in urban areas. However, for our secondary customer of more recreational users, we have a rugged variant that features a larger tread for rougher terrain. Finding a common interface allows us to save a large amount of time and money during manufacturing and assembly. When looking at our foldable scooter, we saw that 6 different screws and nuts were being used as part of the product, and we looked to simplify all fasteners and nuts down to 1 common screw and nut representing 1 common interface. The 1 common screw and nut can be used during manufacturing assembly of both the primary variant as well as the more rugged variant of the scooter. When comparing assembly sequences of our product family, we can see that modifying the sequence and installing wheels last enables delayed product differentiation.
Analyzing the assembly to find the highest impact part, handle has the highest assembly time, which is a purchased part. Wheel and flange comes next with high assembly time and functional importance. These parts were selected based on its importance on quad chart and potential for redesign. Flange and wheel have high functional importance and cost in the assembly, justifying its selection for redesign. Starting with the flange, it took 20.95 seconds for its assembly on the base plate. Modifying the design, hole diameter was changed to match with the slot so that the same fasteners can be used in both places. Flange's projected portion was cut out on the base plate to easily locate and orient flange for welding, which was otherwise held by fixture support, increasing the assembly time. This does not affect the part's function, but slightly increases the base plate's cost. For the wheel, it used to take 22.89 seconds to assemble it. After redesign, spacers were eliminated to reduce part count. Instead, the wheel was embossed and the shaft hole was chamfered symmetrically for all wheels. This modification does not affect its function, but increases the cost of the wheel, which is compensated by a reduced assembly time of 17.5 seconds.
For design for automated assembly, we chose the wheel bracket, compression spring, and fasteners to be improved. As you can see in the function component mapping matrix, these 3 components share many of the same functions, giving us a great opportunity to consolidate this subassembly down to 1 part.
Here you can see the before design of the subassembly on the front wheel. You can notice how 2 springs are used, 2 smaller brackets, and 3 total fasteners. This would normally cost $12.62 for handling and insertion. In this after design, you can see 1 wheel bracket that is used to connect the wheel to the handle frame using only 1 part. This design covers DFA1 by reducing part counts to only 1, reducing the amount of fasteners down from 3 to 1, which would be DFA2. DFA5 of reducing part variety is met by creating one symmetrical bracket rather than 2 brackets and 2 springs. And with no springs, we also eliminate any chance for tangling or nesting like DFA8 points out. The part function is not affected, as the spring that was in the original design played no role in the movement of the scooter. This also decreases the manufacturing cost, as there are less parts required to be manufactured. This brings the total assembly cost down to $4.59, which is much less than the previous cost of $12.62.
We completed the process selection matrices to analyze the base sheet and the wheel. For the base sheet, we decided on a tolerance of 0.38 millimeters across the length, which is standard for sheet metal parts according to this documentation from Protolabs. This allows for the alignment of the brake assembly on the back of the base sheet. Sheet forming and machining are ideal for the base plate, whereas additive manufacturing did not meet the economic batch size. For the wheel, we chose a radial tolerance of 0.5 millimeters to prevent wobbling. Given the high section thickness of the high-density polyethylene wheel, machining was the only ideal option for manufacturing.
Here we have our DfM for our first part, the flange. On the right, you can see that we have the DfM Pro screenshot, which we used to implement changes. You can also see the estimated cost at 250,000 parts and the cost without profit margin using the Hub's prediction and extrapolation. Using the same methods described in the prior slide, you can see that we implemented multiple changes. We combined the base plate and the flange, decreased the thickness, increased the bending radius on the flange, and deleted the hem on the base plate section. The estimated cost at 250,000 parts is shown, along with the cost without profit margin. We determined that this proved to be more cost-effective for manufacturing the scooter. This slide just shows the DfM Pro for the previous slide. The portion talking about the hem radius, opening, and thickness is important to note since we implemented a few changes involving these aspects.
Here is our DfM for our second part, the wheel. We can see that the total cost is $57.92 per part with injection molding. After running the part through DfM Pro, the recommendations for DfM were to create uniform wall thickness, increase the mold wall thickness for inside the axle hole, and increase the draft angle as seen in these screenshots from the DfM Pro. After modifying our part to satisfy the recommendations provided by DfM Pro, the new cost of our modified wheel is $57.93 per part.
We plan to offer a number of services to both reduce the environmental impact of our product as well as to improve the overall customer experience. We will offer end-of-life recycling by manufacturing the scooter out of easily recyclable materials such as metal and plastic and allowing customers to send their old product back in to be recycled when they are done with it. We hope to improve the environmental impact of the scooter. We will also provide maintenance information and assistance, as well as offer a warranty and an individual part exchange program, allowing customers to more easily fix their scooter and avoid buying a completely new one if only one part breaks. This will both reduce the environmental impact of the product by ensuring that as little of it goes to waste as possible, as well as help to reduce the cost to the customer. Our design for manual assembly of both the wheel and the flange managed to save time, over 5 seconds per part for the wheel and over 6 seconds per part for the flange. Additionally, our design for automated assembly saved over $8 per part. However, our design for manufacturing redesign for both the flange and the wheel cost more money per part due to additional material costs. Our manufacturing adjustments that we made came with cost increases. This leaves room for potential further redesign. Another potential redesign is of the handlebars to increase manufacturing and assembly efficiency. Our next steps would be to do design for manufacturing for the other parts of the scooter. Our design for manual assembly of our wheel and flange managed to save time per part, over 5 seconds per part for the wheel and over 6 seconds per part for the flange. Additionally, our redesign for automated assembly of the front wheel saved over $8 per part in assembly costs. However, due to additional material costs associated with the redesign, our design for manufacturing of the flange and the wheel added cost per part. These manufacturing adjustments that came with cost increases leave room for potential further redesign. We see further potential redesign of the handlebars that could increase manufacturing and assembly efficiency. However, our next steps are to do design for manufacturing for the other parts that we didn't touch on. If we were to start this all over again, we would put more emphasis on the function component mapping matrix, as a lot of our work in the redesigning was based off of our work there.